As you rest peacefully tonight, you are surrounded by an invisible force field extending thousands of miles into space, generated by currents of molten iron flowing deep beneath your feet, deflecting harmful solar radiation that would otherwise strip away our atmosphere and make Earth as barren as Mars. This magnetic field, the magnetosphere, is so fundamental to life's existence that without it, you wouldn't be here to contemplate it. Yet it remains completely imperceptible to human senses, detectable only through instruments or through the spectacular auroras it creates when solar particles interact with its invisible boundaries. Tonight, as you drift towards sleep, you'll discover how Earth's magnetic field is generated by a planetary dynamo operating in the liquid outer core thousands of miles below, why the magnetic poles don't align with the geographic poles and slowly wander across the planet's surface, how the magnetosphere deflects the solar wind and protects our atmosphere from erosion, what happens during magnetic field reversals when north and south poles flip, how compasses have guided navigation for centuries using this invisible field, and why understanding Earth's magnetism reveals profound truths about our planet's interior structure, its protective systems, and the cosmic environment we inhabit. Earth's magnetic field resembles that of a giant bar magnet tilted about 11 degrees from the planet's rotation axis, with field lines emerging from the southern hemisphere, arcing through space and re-entering in the northern hemisphere. But unlike a bar magnet, Earth's field isn't created by permanent magnetism in rocks. The planet's interior is far too hot for rocks to retain permanent magnetization. Instead, our magnetic field is generated by electric currents flowing in the outer core, a layer of liquid iron and nickel about 1,400 miles thick, located roughly 1,800 to 3,200 miles beneath your feet. The strength of Earth's magnetic field at the surface averages about 50 microtesla, 0.5 Gauss, strong enough to orient compass needles but far weaker than a refrigerator magnet. Yet this seemingly weak field extends tens of thousands of miles into space on the night side of Earth, and compresses to perhaps 40,000 miles on the day side, where it pushes back against the solar wind. This vast magnetic bubble, the magnetosphere, is the shield that has protected Earth's atmosphere and life for billions of years. The magnetic field isn't uniform or stable. It varies in strength and direction across Earth's surface and changes over time. Some regions have stronger fields, others weaker. The magnetic North Pole, where field lines point straight down, wanders continuously, currently drifting northward through the Canadian Arctic toward Siberia at about 30 miles per year, much faster than its historical average. These movements reflect the dynamic processes occurring in Earth's liquid outer core, where the magnetic field originates. Without Earth's magnetic field, the solar wind, a stream of charged particles constantly flowing from the Sun at speeds approaching 1 million miles per hour, would directly impact our atmosphere. Over millions of years, this bombardment would gradually strip away atmospheric gases, particularly lighter elements like hydrogen and oxygen, eroding the air we breathe and the water in our oceans. Mars, which lost its global magnetic field billions of years ago, provides a cautionary example. Its atmosphere has been largely stripped away by the solar wind, leaving only 1% of Earth's atmospheric pressure, and making the surface inhospitable to life as we know it. The magnetic field also protects life from harmful cosmic rays, high-energy particles from exploded stars, and other cosmic sources that can damage DNA and increase cancer risks. While the atmosphere provides some shielding, the magnetosphere deflects many cosmic rays before they can reach the upper atmosphere, reducing radiation exposure for organisms at Earth's surface. Astronauts leaving Earth's protective magnetic field face increased radiation risks, requiring shielding on spacecraft traveling to the Moon, Mars, or beyond. Evidence of Earth's ancient magnetic field is preserved in rocks. When molten lava cools and solidifies, magnetic minerals within the rock align with the prevailing magnetic field and remain frozen in that orientation. By studying these paleomagnetic signatures in rocks of different ages, scientists have reconstructed Earth's magnetic history, discovering that the field has existed for at least 3.5 billion years and has reversed polarity, north and south pole switching, hundreds of times throughout Earth's history, with the last reversal occurring about 780,000 years ago. As you prepare to explore Earth's magnetic field tonight, rest in appreciation that this invisible shield has been operating continuously since early in Earth's history, quietly protecting the atmosphere and life from cosmic hazards, guiding migrating animals and human navigators, and creating the spectacular auroral displays that paint polar skies when solar particles interact with the magnetosphere's boundaries, demonstrating that some of Earth's most important features remain completely invisible to our senses, yet profoundly shape the habitability of our planet and our ability to exist as conscious beings contemplating the protective embrace of our magnetic home. The planetary dynamo, how Earth generates its magnetic field. Descend now thousands of miles into Earth's interior to discover the geodynamo, the self-sustaining process that creates and maintains our planet's magnetic field through the motion of electrically conductive liquid iron in the outer core, demonstrating that Earth functions as a natural electromagnet powered by heat escaping from the planet's formation and from radioactive decay, creating a magnetic field through the same electromagnetic principles that power electric motors and generators. Earth's interior is layered like an onion, the thin crust just a few miles thick under oceans, up to 40 miles thick under continents, sits atop the solid rocky mantle extending down about 1,800 miles. Below the mantle lies the core, divided into two regions, the liquid outer core, 1,800 to 3,200 miles deep, composed primarily of molten iron with some nickel and lighter elements, and the solid inner core, 3,200 to 3,950 miles deep, Earth's center, made of iron and nickel crystallized under immense pressure, despite temperatures exceeding 9,000 degrees Fahrenheit, as hot as the Sun's surface. The outer core is where Earth's magnetic field originates. This layer consists of liquid iron at temperatures around 7,000 to 9,000 degrees Fahrenheit, under pressures millions of times atmospheric pressure. Despite the extreme conditions, the iron remains liquid because the temperature exceeds the melting point at that pressure. This liquid iron is electrically conductive. Electric current can flow through it just as through copper wires, and it's in constant motion driven by heat escaping from the even hotter inner core below and the cooler mantle above. The motion of conducting fluid in the outer core creates electric currents through a process called convection. Hot iron near the inner core boundary is less dense and rises toward the mantle, while cooler iron near the mantle boundary is denser and sinks. This creates convection cells, circulation patterns similar to boiling water but operating on planetary scales over centuries and millennia rather than seconds. As this conducting fluid moves through existing magnetic fields, it generates electric currents, and these currents in turn create magnetic fields, a self-reinforcing cycle called the geodynamo. The Coriolis effect from Earth's rotation organizes the convection patterns in the outer core. Rising and falling iron doesn't move in simple vertical columns, but curves due to the planet's spin, creating helical spiral flow patterns aligned roughly with Earth's rotation axis. These organized flows are crucial for generating a coherent planetary magnetic field, rather than a chaotic jumble of weak local fields. The rotation provides the organization that transforms random convection into the structured flows necessary for maintaining a dipolar field, like a bar magnet with north and south poles. The geodynamo is self-sustaining once established. Magnetic fields in the outer core induce electric currents in the moving iron, and these currents generate magnetic fields that reinforce the original fields, creating a positive feedback loop. Energy comes from Earth's internal heat, both primordial heat from the planet's formation 4.5 billion years ago and heat from radioactive decay of elements like uranium, thorium and potassium in the mantle and core. As long as heat continues escaping from Earth's interior, which it will for billions of years, the outer core will remain liquid and convecting, maintaining the geodynamo. Computer simulations of the geodynamo solve complex equations describing fluid dynamics, electromagnetic induction, and heat transfer in the outer core. These simulations can reproduce Earth's magnetic field characteristics: the dipolar structure, the strength, the slow changes over time, and even the occasional reversals of polarity. The simulations confirm that the basic theory is correct. Earth's magnetic field really does result from convecting liquid iron in the outer core, and the mathematics of magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields, successfully describes this planetary scale process. The cooling of the inner core contributes energy to the geodynamo. The inner core is slowly growing as iron crystallizes out of the liquid outer core, releasing latent heat, the energy released when liquid solidifies, and lighter elements that get excluded from the solid iron crystals. These lighter elements are buoyant and drive convection in the outer core, providing additional energy to maintain the geodynamo beyond what thermal convection alone would provide. This process will continue as long as the core continues cooling, estimated to be for at least several billion years. Other planets show varying magnetic field characteristics based on their interior structure and dynamics. Jupiter has the strongest planetary magnetic field in the solar system, generated by convection in a layer of metallic hydrogen under extreme pressure deep in the planet's interior. Mercury has a weak but detectable magnetic field despite its small size. Venus and Mars lack global magnetic fields currently, though Mars had one in its past, possibly because their cores aren't convecting properly or have solidified. These variations demonstrate that planetary magnetic fields require specific conditions, liquid conducting regions undergoing organized convection that not all planets maintain. The geodynamo occasionally reverses polarity, switching magnetic north and south poles. The last reversal occurred about 780,000 years ago, and reversals appear to happen irregularly every few 100,000 years on average. During a reversal, the magnetic field weakens dramatically, perhaps to 10% of normal strength, becomes more complex with multiple poles appearing temporarily, then re-establishes with opposite polarity. The process takes several thousand years, and while Earth's magnetic protection weakens during reversals, life has survived hundreds of previous reversals without mass extinctions, suggesting that the atmosphere provides enough shielding even when the magnetic field is weak. As you rest peacefully tonight, imagine the vast ocean of molten iron flowing far beneath you in patterns organized by Earth's rotation. Electric currents circulating through this conducting metal, magnetic fields generated by those currents reinforcing themselves through electromagnetic induction, and the entire system maintaining itself through geophysical processes that have operated for billions of years, creating the invisible shield that extends into space around you while you sleep safely beneath its protective embrace, demonstrating that planetary habitability depends on processes operating at scales and depths far removed from the surface, yet absolutely crucial for maintaining the conditions that allow life to exist and flourish. The magnetosphere, Earth's space weather shield. Rise now into the space around Earth, where the magnetic field extends thousands of miles, creating the magnetosphere, a vast magnetic bubble that stands between our planet and the harsh space environment, deflecting the solar wind, trapping energetic particles in radiation belts, and creating the dynamic boundary regions where solar and terrestrial magnetic fields interact in ways that produce some of space physics' most dramatic phenomena, including the auroras that illuminate polar skies. The magnetosphere isn't shaped like Earth's magnetic field would be in isolation, which would extend symmetrically in all directions like a bar magnet's field. Instead, it's compressed on the side facing the sun and stretched into a long tail on the night side by the solar wind. The constant stream of charged particles flowing from the sun at speeds approaching 1 million miles per hour. The result is a teardrop-shaped magnetic cavity extending perhaps 40,000 miles sunward, but stretching hundreds of thousands of miles away from the sun, with Earth sitting inside this magnetic cocoon. The boundary between the magnetosphere and the solar wind is called the magnetopause, a dynamic, constantly moving surface where the pressure of Earth's magnetic field equals the pressure of the solar wind. When solar wind strengthens during solar storms, it compresses the magnetosphere and the magnetopause moves inward closer to Earth. When solar wind weakens, the magnetopause expands outward. This boundary isn't smooth, but ripples with waves and instabilities created by the interaction of solar wind plasma with the magnetospheric magnetic field, creating space weather conditions that vary constantly. Ahead of the magnetopause sits the bow shock, a region where the supersonic solar wind slows down dramatically as it encounters the obstacle of Earth's magnetic field. Like the shock wave that forms ahead of a supersonic aircraft, the bow shock represents the transition from supersonic to subsonic flow, with the solar wind's kinetic energy converting partly to heat and turbulence. The region between bow shock and magnetopause, called the magnetosheath, contains heated, compressed, turbulent solar wind plasma that flows around the magnetosphere like water flowing around a rock in a stream. The Van Allen radiation belts, discovered in 1958 by America's first satellite, Explorer 1, are regions where energetic particles become trapped by Earth's magnetic field. The inner belt, centered about 2,000 to 4,000 miles above Earth's surface, contains mainly protons. The outer belt, centered about 9,000 to 15,000 miles up, contains mainly electrons. These belts form because charged particles spiral along magnetic field lines and bounce between northern and southern hemispheres, becoming trapped in the magnetic field structure. The radiation levels in these belts are high enough to damage satellites and pose risks to astronauts, requiring spacecraft to either stay below, pass through quickly, or operate between the belts. The magnetotail, the long extension of the magnetosphere on the night side of Earth, plays a crucial role in storing energy from the solar wind and releasing it during magnetic substorms. Solar wind can't penetrate the magnetopause directly, but it can transfer energy to the magnetosphere through magnetic reconnection, a process where magnetic field lines break and reconnect in new configurations, transferring energy and plasma across the boundary. Energy stored in the stretched magnetotail is episodically released, accelerating particles toward Earth and creating the auroral displays that illuminate polar skies during geomagnetic storms. The magnetic cusps, regions near the poles where magnetic field lines come straight down rather than arcing through space, represent areas where the magnetosphere is more vulnerable to solar wind penetration. Here, field lines connect directly from space to Earth's surface without forming closed loops in the magnetosphere, allowing solar wind particles direct access to the upper atmosphere along these open field lines. The cusps contribute to auroral displays and represent important regions for transferring energy and particles between the solar wind and the magnetosphere. Magnetic storms, major disturbances in Earth's magnetic field, occur when especially intense solar wind or coronal mass ejections from the Sun interact with the magnetosphere. During storms, the magnetosphere compresses dramatically, energetic particles precipitate into the atmosphere, creating intense auroras. Electric currents strengthen in the upper atmosphere and along the ground, and satellite operations can be disrupted by the disturbed space environment. The largest magnetic storms can interfere with power grids, communications, GPS navigation, and spacecraft operations, demonstrating that space weather affects technological systems at Earth's surface. The magnetosphere protects satellites and astronauts in low Earth orbit, a few hundred miles altitude, from much of the solar wind's effects. The International Space Station orbits within the magnetosphere's inner regions, gaining significant protection from Earth's magnetic field. Astronauts traveling beyond low Earth orbit to the Moon, or eventually Mars, leave this magnetic protection and face higher radiation exposure from solar particles and cosmic rays, requiring spacecraft shielding and careful mission timing to avoid major solar storms. Magnetic reconnection at the magnetopause and in the magnetotail represents one of space physics' most important processes. When oppositely directed magnetic field lines encounter each other, solar wind magnetic fields facing one direction, Earth's magnetic fields facing one direction, another, they can break and reconnect in a process that converts magnetic energy to particle kinetic energy very efficiently. This process accelerates particles to high energies, heats plasma, and transfers energy and mass across magnetic boundaries, playing crucial roles in substorms, auroras, and the overall dynamics of the magnetosphere. The magnetosphere isn't unique to Earth. Other planets with magnetic fields have their own magnetospheres, each with characteristics reflecting the planet's magnetic field strength and the solar wind conditions at that distance from the Sun. Jupiter's enormous magnetosphere extends millions of miles and contains trapped radiation more intense than Earth's. Saturn, Uranus and Neptune also have significant magnetospheres. Mercury has a miniature magnetosphere, while Venus and Mars lack global magnetic fields and consequently don't have magnetospheres, leaving their atmospheres more exposed to the solar wind. As you drift towards sleep tonight, imagine Earth's magnetosphere as an invisible shield surrounding the planet, its boundaries constantly buffeted by the solar wind, particles trapped in radiation belts circling the planet, energy being stored and released in the magnetotail, and the entire dynamic system responding continuously to changing solar conditions while maintaining the protective bubble that shields our atmosphere and surface from the harsh space environment, demonstrating that living on Earth means inhabiting not just a rocky planet, but a magnetic sanctuary carved out of the solar wind's domain, a cosmic oasis where magnetic fields create the conditions necessary for maintaining an atmosphere, liquid water, and the delicate balance of conditions that makes life possible. Magnetic navigation. Following invisible lines. Discover now how Earth's magnetic field has guided navigation for over 1,000 years, how compass needles align with invisible field lines to point roughly northward, why magnetic declination varies with location and must be accounted for in precise navigation, how animals from birds to sea turtles sense the magnetic field to navigate across thousands of miles, and how this ancient force continues serving modern purposes, from smartphone compasses to the magnetometers that help spacecraft orient themselves in the void. The magnetic compass, a magnetized needle free to rotate horizontally, is perhaps the simplest yet most historically important application of Earth's magnetic field. The needle aligns with local magnetic field lines, pointing approximately toward magnetic north. Chinese navigators used compasses by the 11th century, and the technology spread to Europe by the 13th century, revolutionizing maritime navigation by providing reliable directional information even when clouds obscured the sun and stars. For centuries, the compass was the primary tool, allowing ships to navigate across oceans with confidence, enabling the age of exploration and transforming human civilization through improved navigation. Magnetic declination, the angle between true north, the geographic pole, and magnetic north, the direction a compass points, varies with location and time, requiring navigators to correct compass readings for accurate position finding. In some locations, declination is near zero, and compasses point almost exactly toward true north. In other locations, declination can exceed 20 degrees east or west, creating significant navigation errors if not accounted for. Aeronautical and nautical charts include magnetic declination information for various locations, and careful navigators apply these corrections when using magnetic compasses for precision navigation. The wandering of magnetic north creates a need to update declination values periodically. Because the magnetic pole moves continuously and the magnetic field's structure changes over years and decades, declination at any given location changes slowly, perhaps a degree per decade in many areas. Modern charts and navigation systems incorporate these changes, but historic declination values are incorrect for current navigation, creating potential confusion when using old maps or navigation tables that don't account for secular variation, long-term changes in magnetic field direction and strength. Magnetic inclination, the angle at which field lines tilt into or out of Earth's surface, varies from 0 at the magnetic equator, where field lines run horizontally, to 90 degrees at the magnetic poles, where field lines point straight down or up. Animals that sense magnetic fields may use inclination along with field strength as components of a magnetic map, allowing them to determine latitude from magnetic information alone. Compasses that measure inclination dip needles historically helped geophysicists map magnetic field structure and locate magnetic poles. Many animals possess magnetoreception, the ability to sense magnetic fields, using it for navigation during migration or local movements. Sea turtles hatching on beaches navigate to the ocean, then spend years crossing ocean basins, eventually returning to the same beaches to nest, apparently using magnetic information to maintain bearing and recognize specific ocean regions by their magnetic signatures. Salmon return from ocean feeding grounds to the exact streams where they were born, likely using magnetic information along with other cues like smell. Migrating birds use magnetic fields along with celestial cues to maintain bearing during long-distance flights across featureless ocean or barren terrain. The mechanism of magnetic sensing varies among animals. Some species have magnetite iron oxide crystals in their bodies, in birds' beaks, in fish brains, in the abdomens of migrating insects, that may act as physical sensors responding to magnetic fields and connecting to nerves that transmit magnetic information to the brain. Other species may use chemical magnetoreception through cryptochromes, the same proteins involved in bird navigation discussed previously, where quantum mechanical effects in these molecules create signals that vary with magnetic field orientation, allowing animals to literally see magnetic field patterns overlaid on their vision. Human navigation has largely transitioned from magnetic compasses to GPS and other satellite-based systems, but magnetic compasses remain important backups and primary navigation tools in situations where electronics fail or are unavailable. Hikers, sailors, and military personnel still train in magnetic compass use, recognizing that while GPS is more accurate and convenient when working, a simple compass requires no batteries, doesn't break easily, and provides reliable directional information as long as you account for declination and avoid local magnetic disturbances from metal objects or electrical devices. Smartphones contain miniature magnetometers, solid-state sensors that measure magnetic field strength and direction, that provide compass functionality in navigation apps. These sensors must calibrate themselves by measuring the magnetic field from multiple orientations. The figure 8 motion you make when your phone asks you to calibrate its compass, to separate Earth's magnetic field from magnetic interference from the phone's own components. Once calibrated, These miniature magnetometers provide compass heading information that navigation apps combine with GPS data to determine both position and orientation. Spacecraft use magnetometers for attitude determination, figuring out which way they're pointing in space. By measuring the direction of Earth's magnetic field, or another planet's field, spacecraft computers can determine orientation relative to the planet. This is particularly useful for satellites in low Earth orbit, where the magnetic field is strong enough to provide clear signals, and where magnetic torque rods, coils that generate magnetic fields to push against the planetary magnetic field, can provide attitude control without expending propellant. Magnetic anomalies, local variations in field strength caused by concentrations of magnetic minerals in Earth's crust, created historical navigation hazards when compass needles deflected unexpectedly near iron-rich rock formations or magnetic ore deposits. Maps of magnetic anomalies help modern navigators avoid confusion in regions where crustal magnetic fields significantly distort the larger-scale structure of Earth's main magnetic field. These anomalies also provide clues about subsurface geology, with prospectors using magnetic surveys to locate ore deposits and geologists using them to map hidden rock formations. The magnetic field's role in navigation demonstrates how Earth's geophysical features shape not just physical landscapes, but also the behavior and biology of organisms. The field that protects our atmosphere from solar wind erosion also provides navigational information that countless species use to accomplish migrations and movements crucial for their survival. That the same magnetic field serves both protective and informational functions demonstrates the multiple ways that planetary features contribute to habitability and enable the ecological complexity we observe. As you rest peacefully tonight, compasses around the world point toward magnetic north. Animals sense field lines and inclination angles to orient themselves in darkness or featureless environments. Smartphones measure magnetic heading to show users which direction they face, and spacecraft use magnetometers to maintain proper orientation, all relying on the same invisible field generated thousands of miles beneath Earth's surface, demonstrating that this ancient feature of our planet continues serving vital functions in both natural systems and human technology, creating an information resource as valuable as its protective functions, and demonstrating that Earth's magnetic field represents far more than passive shielding, instead functioning as an active system that shapes life and enables capabilities that wouldn't exist without this invisible but fundamental planetary feature. When poles flip, magnetic reversals. Through time. Journey now through Earth's magnetic history, discovering that the poles have switched hundreds of times over the planet's 4.5 billion year existence, that the last reversal occurred 780,000 years ago, and the next could happen any time in the next several thousand years or longer, that during reversals the field weakens dramatically and may become temporarily chaotic with multiple poles, and that understanding reversals reveals both the dynamic nature of the geodynamo and the resilience of life in adapting to dramatic changes in Earth's magnetic environment. The record of past magnetic reversals is preserved in rocks through paleomagnetism. When lava cools, magnetic minerals within the rock align with Earth's magnetic field and remain locked in that orientation. Ocean floor rocks provide an especially clear record, because new crust forms continuously at mid-ocean ridges through volcanic activity, then spreads away from the ridges as seafloor spreading proceeds. This creates a magnetic striping pattern symmetrical on both sides of ridges, bands of normal polarity, same as today, alternating with bands of reversed polarity, opposite from today, recording the magnetic field's behavior over millions of years as new ocean floor formed and spread. Geologists have dated these magnetic stripes and constructed a chronology of reversals extending back hundreds of millions of years. The pattern is irregular. Periods of predominantly normal polarity with occasional reversals. Periods of predominantly reversed polarity with occasional flip-flops back to normal. And even supercrons when polarity remained stable for tens of millions of years. The most recent normal polarity period, called the Brunnerschron, has lasted 780,000 years. Before that, the Matuyama reversed chron lasted from 780,000 to 2.6 million years ago, with several brief normal polarity excursions during that time. The frequency of reversals has varied throughout Earth's history. During the Cretaceous period, roughly 120 to 83 million years ago, the magnetic field remained normal for about 40 million years without any reversals, the Cretaceous normal superchron. At other times in Earth's history, reversals occurred frequently, perhaps every few 100,000 years on average. This variability suggests that the geodynamo can operate in different regimes, sometimes producing a stable field that resists reversal, other times producing a less stable field, more prone to polarity changes. The process of reversal isn't instantaneous, but takes several thousand years to complete, though this is geologically rapid. During a reversal, the magnetic field weakens substantially, perhaps to 10% of its normal strength or even less. The dipolar structure, like a bar magnet with two poles, breaks down and the field becomes more complex, possibly with multiple magnetic north and south poles appearing simultaneously at various locations. Eventually, one set of opposite polarity poles strengthens and becomes dominant, establishing the new polarity, and the field gradually rebuilds to normal strength over several thousand years following the reversal. The cause of reversals likely relates to instabilities in the geodynamo. Computer simulations of core convection and magnetic field generation occasionally produce spontaneous reversals when particular patterns of convection arise that disrupt the main dipolar field. The exact trigger mechanism remains uncertain. It may involve stochastic random fluctuations in core flow reaching thresholds that initiate reversal, or it may involve interactions between the core and mantle that periodically destabilize the geodynamo. Current knowledge suggests reversals emerge naturally from the chaotic dynamics of the fluid core, rather than being triggered by external events like asteroid impacts. Life has survived hundreds of reversals without mass extinctions directly attributable to magnetic field changes, suggesting that even when the field weakens dramatically, the atmosphere provides sufficient protection from cosmic radiation to prevent catastrophic effects. Some studies have proposed correlations between reversals and species turnover or climate changes, but clear causal connections remain debatable. The most significant impact would be increased radiation exposure during the reversal's low field phase, but this would mainly affect high-altitude regions, and wouldn't necessarily threaten most organisms at or near sea level where the atmosphere provides substantial shielding. Modern technological systems might be more vulnerable to reversals than biological life. During the low field phase of a reversal, the magnetosphere weakens and becomes less effective at deflecting the solar wind, potentially allowing more solar particles to reach low Earth orbit satellites and creating stronger magnetic storms. Power grids, communication systems, and navigation that depend on magnetic field stability could be disrupted. However, the gradual nature of reversals would provide time for human societies to develop mitigation strategies and adapt systems to function with a weaker or more complex magnetic field. The current state of Earth's magnetic field has led some scientists to speculate that a reversal might be approaching. The field has weakened by about 10% over the past 180 years, and the magnetic North Pole is moving more rapidly than historically typical. The South Atlantic anomaly, a region off the coast of Brazil where the magnetic field is significantly weaker than elsewhere, has been growing. These changes might represent precursor signs of an approaching reversal, or they might simply be normal fluctuations that will reverse without leading to a full polarity flip. Predicting reversals remains impossible with current knowledge. One could begin tomorrow or not for tens of thousands of years. Studying reversals helps scientists understand the geodynamo's behavior and test computer models. Successfully simulating reversals requires models that capture the core's complex fluid dynamics and magnetic field generation correctly. Models that reproduce Earth's current magnetic field structure, its slow variations and spontaneous reversals, are more likely to be correct than models that can't produce these behaviors. Reversals thus serve as natural experiments that test our understanding of deep Earth processes that can't be directly observed but can be inferred from their surface manifestations. The magnetic field's ability to reverse yet maintain itself for billions of years demonstrates the geodynamo's robustness. The system can experience major disruptions, yet self-repair and continue operating. This resilience ensures that Earth has maintained magnetic protection throughout most of its history, despite the chaotic nature of core convection that occasionally produces reversals. The long-term stability, combined with occasional reversals, characterizes a dynamic system that's stable on average, but not rigidly fixed, allowing variability while maintaining essential function. As you drift peacefully into sleep tonight, rest assured that even if a magnetic reversal begins tomorrow, the process would unfold over thousands of years, allowing ample time for adaptation and mitigation, and that life has demonstrated its ability to survive these transitions hundreds of times before, suggesting that magnetic reversals, while dramatic from a geophysical perspective, don't pose existential threats to the biosphere, demonstrating Earth's resilience and the multiple layers of protection, atmosphere plus magnetic field, that ensure habitability even when one layer temporarily weakens, proving that our planet's life support systems have redundancy and resilience built into their structure through billions of years of planetary evolution. The magnetic future, protection for eons to come. Rest now in contemplation of Earth's magnetic future, how the geodynamo will continue operating for billions of years as the core slowly cools, what eventual loss of the magnetic field millions of years hence might mean for Earth's environment, how understanding magnetism helps us appreciate Mars's fate as a cautionary example, what magnetic field research reveals about planetary habitability in general, and why this invisible shield represents one of the fundamental requirements for maintaining the stable conditions that allow complex life to evolve and persist. The geodynamo will continue operating for billions of years because Earth's core retains enormous heat that will take geological ages to dissipate. The inner core is slowly growing as iron crystallizes from the liquid outer core, releasing latent heat and light elements that drive convection. Radioactive decay in the mantle and possibly the core continues producing heat. These heat sources will maintain the temperature difference between core and mantle necessary to drive outer core convection for at least several billion years. Possibly longer than the Sun will continue supporting life on Earth's surface through its solar energy. Eventually, perhaps 5 to 10 billion years in the future, the outer core will cool enough to solidify completely or reduce convection to levels insufficient for maintaining the geodynamo. At that point, Earth's magnetic field would disappear, leaving the planet without its primary space weather shield. The solar wind would then directly impact the upper atmosphere, gradually eroding atmospheric gases over millions of years. However, this timeline extends so far into the future that the Sun's evolution into a red giant, expected in about 5 billion years, will likely sterilize Earth's surface long before magnetic field loss threatens habitability through atmospheric erosion. Mars provides a sobering example of what happens when a planet loses its magnetic field. Mars had a global magnetic field early in its history, evidenced by magnetized regions of ancient crust, probably generated by a core geodynamo similar to Earth's. But Mars cooled faster than Earth due to its smaller size. Smaller planets have higher surface-to-volume ratios and radiate heat more efficiently. By about 4 billion years ago, Mars's core had cooled enough that the geodynamo ceased. The global magnetic field disappeared, and the solar wind began eroding the atmosphere. Over billions of years, atmospheric erosion transformed Mars from a warmer, wetter world with liquid water on its surface into the cold, dry planet we observe today. The loss of atmospheric pressure prevented liquid water from remaining stable at the surface. The loss of greenhouse gases cooled the planet further, while Mars's story involved multiple factors, including its distance from the Sun and lack of plate tectonics to recycle atmospheric gases. The loss of magnetic protection played a crucial role in allowing atmospheric erosion that made the surface inhospitable to life as we know it. Venus, despite lacking a magnetic field currently, maintains a thick atmosphere because its proximity to the Sun provides stronger gravity, and because atmospheric erosion occurs slowly enough that volcanic outgassing has been able to maintain atmospheric pressure despite solar wind erosion. This demonstrates that magnetic fields, while beneficial for atmospheric retention, aren't absolutely necessary if other factors, like high gravity, volcanic activity, and distance from the Sun are favorable. However, Earth-like planets at Earth-like distances from their stars likely need magnetic fields for long-term atmospheric stability. The search for habitable exoplanets increasingly considers magnetic fields as an important criterion. A rocky planet in the habitable zone around its star might seem promising, But if it lacks a magnetic field, its atmosphere might erode over millions of years, eliminating surface habitability. Scientists are developing methods to detect exoplanet magnetic fields through their interactions with stellar winds or through radio emissions similar to Jupiter's, though detecting fields around Earth-sized exoplanets remains technically challenging with current instruments. Earth's magnetic field also serves research purposes in understanding planetary interiors. By studying magnetic field variations and how they relate to core processes, geophysicists learn about the structure and dynamics of Earth's deep interior that can't be directly observed. Seismology reveals layer boundaries and major structural features, but magnetic field studies provide information about composition, temperature, and flow patterns in the liquid outer core, complementing seismic data to create a more complete picture of Earth's interior. The possibility of artificially generating magnetic fields to protect Mars or other planets has been discussed in the context of terraforming, hypothetical future attempts to make other worlds habitable. One proposal involves positioning a magnetic shield at the Mars-Sun L1 Lagrange point to deflect solar wind from Mars, potentially allowing the atmosphere to rebuild over centuries or millennia. While technologically far beyond current capabilities and questionable in terms of ethics and practicality, these concepts demonstrate that humans are beginning to think about magnetic fields as engineerable features of planetary environments rather than just as givens. Understanding Earth's magnetic field helps us appreciate our planet's unique combination of properties that maintain habitability. The field requires a liquid metallic layer undergoing organized convection. Not all planets develop or maintain these conditions. Earth's size is large enough to retain internal heat for billions of years, but small enough to develop plate tectonics that moderates climate. The magnetic field works synergistically with other protective systems: the atmosphere that shields against radiation, the ozone layer that blocks ultraviolet light, and the moon that stabilizes axial tilt and moderates climate. Remove any one component, and Earth's long-term habitability becomes questionable. As you drift into peaceful sleep tonight, rest in the knowledge that thousands of miles beneath you, molten iron continues its ancient circulation, generating the magnetic field that has protected Earth's atmosphere and life for billions of years, and will continue for billions more. That this invisible shield deflects the solar wind even now as you sleep. That the magnetosphere surrounds our planet like a protective bubble carved from the solar wind's domain, and that you are, in this moment, inhabiting a magnetic sanctuary that makes your existence possible, demonstrating that life on Earth depends not just on what you can see and touch, but on invisible forces operating at planetary scales, creating through geophysical processes the stable conditions necessary for the biosphere to flourish, evolve, and produce conscious beings capable of contemplating the magnetic embrace that sustains them. Sleep well within Earth's magnetic protection, where field lines arc through space thousands of miles above you, where the geodynamo operates continuously in the depths below, where the magnetosphere deflects harmful radiation while allowing the beauty of auroras when solar particles interact with its boundaries, and where this invisible guardian has maintained its watch since early in Earth's history, will continue long into the future, and represents one of the fundamental features that makes our planet not just a rocky world orbiting the Sun, but a living, protected home where complex life can emerge, thrive, and wonder at the invisible forces that make existence possible in a universe where most worlds lack such protection and consequently remain barren, reminding us that we inhabit a rare and precious place whose magnetic field is as essential to our existence as the air we breathe or the water we drink.